Introduction to WebRTC. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving into WebRTC, which stands for Web Real-Time Communication. This is a groundbreaking technology that has fundamentally transformed how we build real-time communication applications on the web. Before WebRTC emerged, developers had to rely on proprietary plugins like Flash or third-party software to enable video calls, voice chats, or peer-to-peer data sharing in web browsers. WebRTC changed all of that by providing a standardized, open-source framework that is built directly into modern web browsers. WebRTC enables direct peer-to-peer communication between browsers without requiring any intermediate servers to relay the actual media streams. This means that when two users are on a video call using WebRTC, their audio and video data flows directly between their devices, resulting in lower latency and better quality. The technology handles three main types of communication: audio streaming for voice calls, video streaming for video conferencing, and arbitrary data transfer for applications like file sharing or gaming. What makes WebRTC particularly powerful is that it is not just about establishing connections. The technology includes sophisticated mechanisms for network traversal, meaning it can work even when users are behind firewalls or NAT devices. It also provides built-in encryption for all communications, ensuring that your video calls and data transfers are secure by default. The codec negotiation capabilities mean that browsers can automatically agree on the best audio and video formats to use based on their capabilities and network conditions. Major companies have embraced WebRTC for their communication platforms. Google Meet, Microsoft Teams, Facebook Messenger, Discord, and countless other services rely on WebRTC to deliver real-time video and audio experiences. The technology has become the de facto standard for browser-based real-time communication, supported by Chrome, Firefox, Safari, Edge, and Opera. This universal support means developers can build applications that work consistently across different platforms and devices without worrying about compatibility issues. WebRTC Architecture Components. Understanding WebRTC's architecture requires grasping its three fundamental APIs that work together to enable real-time communication. Each API serves a distinct purpose and handles different aspects of the communication pipeline. These APIs are designed to be used in combination, creating a complete solution for peer-to-peer communication in web browsers. The MediaStream API is your gateway to accessing local media devices. When you need to capture audio from a user's microphone or video from their webcam, you use this API through the getUserMedia method. This API handles all the complexities of interfacing with hardware devices, requesting permissions from the user, and managing the capture settings. A MediaStream object contains one or more tracks, where each track represents a single media source like an audio channel or video feed. You can manipulate these tracks independently, enabling features like muting audio while keeping video active, or applying filters to video streams before sending them to peers. The RTCPeerConnection API is the heart of WebRTC. This is where the peer-to-peer magic happens. An RTCPeerConnection object manages the complete lifecycle of a connection between two peers. It handles the complex process of establishing a connection through NAT devices and firewalls using ICE candidates. It manages the negotiation of media codecs, ensuring both peers can encode and decode the streams they are exchanging. The API also handles the actual transmission of media streams across the network, managing bandwidth adaptation, packet loss recovery, and jitter buffering to maintain quality even on unreliable networks. The RTCDataChannel API provides a separate pathway for sending arbitrary data between peers. While RTCPeerConnection focuses on audio and video streams, RTCDataChannel gives you a bidirectional communication channel similar to WebSockets, but operating peer-to-peer. You can send text messages, binary data, files, or any other information you need to exchange. The API supports both reliable and unreliable delivery modes, allowing you to choose between guaranteed delivery with retransmission or low latency delivery that tolerates packet loss, depending on your application's needs. Signaling server architecture. While WebRTC enables peer-to-peer communication for media streams, it cannot establish those connections without help. This is where the signaling server comes into play. The signaling server's role is often misunderstood, so it's crucial to clarify what it does and doesn't do. The signaling server does not handle any actual media transmission. Its sole purpose is to help two peers discover each other and exchange the information necessary to establish a direct connection. The signaling process involves exchanging several types of messages between peers. First, peers must exchange SDP offers and answers, which describe the media capabilities and network information of each peer. These SDP messages contain details about what codecs each peer supports, what media streams they want to send or receive, and various parameters for the connection. The signaling server acts as a relay for these messages, taking an offer from one peer and delivering it to the other, and then returning the answer. Beyond SDP exchange, the signaling server also relays ICE candidates between peers. ICE candidates are network addresses where a peer can potentially be reached. Each peer typically discovers multiple candidates representing different network interfaces and pathways. These candidates must be communicated to the remote peer so it can attempt to establish a connection through any available path. The signaling server forwards these candidates as they are discovered, allowing the connection establishment process to proceed efficiently. It is important to understand that WebRTC deliberately does not specify how signaling should work. This is an intentional design, giving developers flexibility to implement signaling in whatever way suits their application. You might use WebSockets for real-time bidirectional communication, implement a polling mechanism with HTTP requests, leverage existing messaging systems like XMPP, or even use carrier pigeons if you are feeling adventurous. The point is that signaling is out-of-band communication that happens over any channel you choose, while the actual media flows peer-to-peer once connections are established. Session Description Protocol. The Session Description Protocol, or SDP, is a text-based format that serves as the foundation for negotiating WebRTC connections. When two peers want to communicate, they must first agree on the parameters of their communication session, and SDP is the language they use to express their capabilities and preferences. Understanding SDP is crucial because it contains all the information needed to establish and configure a media session. An SDP message is structured as a series of lines, each beginning with a single character followed by an equal sign and then the value. The structure follows a specific hierarchy, starting with session-level information that applies to the entire communication session, followed by media-level information that describes each individual media stream. Session-level attributes might include the protocol version, the session originator, and timing information. Media-level attributes describe things like media type, audio or video, transport protocol, port numbers, and codec information. The media description lines in SDP are particularly important. Each media stream gets its own M-line that specifies the media type and the port it will use. Following the M-line are attributes that provide details about that specific media stream. For example, you will see RTP map attributes that map RTP payload types to specific codecs like VP8 for video, or Opus for audio. You will also find FMTP attributes that specify format-specific parameters, such as video resolution limits or audio channel configurations. When establishing a WebRTC connection, one peer creates an SDP offer describing what they want to send and what they are willing to receive. This offer is sent through the signaling server to the remote peer. The remote peer examines the offer, determines what they can support, and generates an SDP answer that describes their own capabilities and confirms what they will accept from the offer. This offer-answer exchange is formalized in the JSEP specification that WebRTC follows, ensuring a standardized negotiation process across all implementations. ICE – Interactive Connectivity Establishment. Interactive Connectivity Establishment, or ICE, is the framework that makes WebRTC work in the real world, where NAT devices and firewalls are ubiquitous. Most users sit behind NAT routers that hide their actual IP addresses from the public internet, and many networks employ firewalls that restrict incoming connections. ICE solves these problems by discovering all possible network paths between two peers and testing them to find working routes for communication. The ICE process begins with candidate gathering. Each peer examines its network interfaces and generates a list of candidates, which are potential addresses where it might be reachable. The first type is host candidates, which are the actual IP addresses of the device's network interfaces. If you have Wi-Fi and Ethernet connected, you might have multiple host candidates. These work great when both peers are on the same local network, allowing direct peer-to-peer communication without any external help. When peers are on different networks, which is typical for internet communication, host candidates usually will not work because of NAT. This is where STUN servers come in. STUN, which stands for Session Traversal Utilities for NAT, helps a peer discover its public-facing IP address and port as seen from the internet. The peer contacts a STUN server, and the server responds with the public address information. This creates server reflexive candidates. When both peers share their server reflexive candidates, they can attempt direct communication through their NAT devices using the public addresses. However, some NAT configurations are particularly restrictive and won't allow direct peer-to-peer connections even with STUN. This is where TURN servers become necessary. TURN, or traversal using relays around NAT, provides a relay service that forwards traffic between peers when direct connection is impossible. A TURN server gives each peer a relayed candidate, which is an address on the TURN server itself. Traffic flows through the TURN server, sacrificing the bandwidth and latency benefits of peer-to-peer communication but ensuring connectivity works in all scenarios. This is the fallback of last resort, used only when no direct path exists. STUN server operations. STUN servers play a vital but lightweight role in WebRTC connectivity. Their purpose is elegantly simple. Tell a client what its public IP address and port look like from the Internet's perspective. This might seem trivial, but it's essential information that a device behind NAT cannot determine on its own. The beauty of STUN is that it's a simple request-response protocol that requires minimal server resources. When a WebRTC peer needs to discover its public address, it sends a STUN binding request to a STUN server. This request is just a UDP packet sent to the server's well-known address. The STUN server receives this packet, examines the source IP address and port from which it arrived, and sends back a binding response containing that information. From the client's perspective, this reveals the NAT mapping that the router created when the outbound packet traversed the NAT device. The client can then share this public address as a candidate with other peers. Google operates free public STUN servers that are widely used in WebRTC applications. The servers stun.l.google.com on port 19302 have become something of a de facto standard for testing and development. These servers handle enormous volumes of traffic, demonstrating how STUN's simple design scales effectively. Because STUN is stateless and each request is independent, servers can handle requests with minimal resource consumption. They do not need to track sessions or maintain state between requests. It is important to understand STUN's limitations. STUN works well with many NAT types, particularly the common cone NAT varieties, but it cannot help with symmetric NAT configurations. In symmetric NAT, the NAT device assigns different port mappings for connections to different destinations, meaning the public address discovered through STUN will not work for connecting to a different peer. STUN also cannot traverse firewalls that block incoming connections regardless of the addressing. For these challenging scenarios, you need TURN servers to provide relay functionality. TURN Server Relay Mechanism. TURN servers represent the heavyweight solution in WebRTC connectivity, providing guaranteed communication, though this comes at the cost of bandwidth and server resources. Unlike STUN servers that simply reflect information, TURN servers actively relay media and data between peers. When you deploy a TURN server, you are essentially providing a proxy service that forwards packets between endpoints that cannot directly connect to each other. The process begins when a peer requests an allocation from a TURN server. This is much more involved than a STUN request. The client authenticates with the server using credentials, typically a username and password, or time-limited credentials based on shared secrets. Once authenticated, the TURN server allocates a relay address for this client. This relay address is a port on the TURN server itself where this particular client can be reached. The server maintains state for this allocation, tracking which relay address belongs to which client. When the peer shares its relayed candidate with a remote peer, and that remote peer decides to use the relayed path, all media flows through the TURN server. The remote peer sends packets to the relay address on the TURN server. The server receives these packets and forwards them to the original client that requested the allocation. Similarly, when the client sends packets toward the remote peer, those packets go to the TURN server first, which then forwards them to their destination. This means every byte of media traverses the TURN server, consuming bandwidth in both directions. The bandwidth implications of TURN are substantial. If you're relaying a video call at 2 megabits per second, the TURN server must handle 2 megabits per second incoming from each peer and 2 megabits per second outgoing to each peer, totaling 4 megabits per second per connection. With multiple simultaneous calls, bandwidth requirements multiply accordingly. This is why TURN servers require significantly more infrastructure investment than STUN servers. You need adequate bandwidth provisioning, powerful hardware to handle the packet forwarding load, and usually redundant servers for reliability. Many WebRTC deployments use commercial TURN services like Twilio's Network Traversal Service or Xerxes rather than operating their own TURN infrastructure. Codec negotiation process. Codec negotiation is a critical component of WebRTC that ensures peers can successfully exchange media even when they support different encoding formats. The process occurs during the SDP offer-answer exchange and determines which codecs will be used for audio and video transmission in the established connection. Understanding this negotiation helps you optimize media quality and ensure compatibility across different browsers and devices. When a peer creates an SDP offer, it lists all the codecs it supports for each media type in order of preference. For audio, you might see Opus listed first, followed by PCMU and PCMA for video. The offer might list VP9, VP8, and H.264 in that order. Each codec listing includes not just the codec name, but also specific parameters that define how it should be used. These parameters might specify the maximum bitrate, the payload type number used to identify this codec in RTP packets, or codec-specific settings like complexity levels for Opus or profile levels for H.264. The answering peer examines the offered codecs and determines which ones it can support. It creates an SDP answer that includes only the codecs it is willing to use, listed again in order of preference. The final codec selection follows a simple rule. The first codec in the answer that matches a codec in the offer is what both peers will use. This means the answering peer has the final say in codec selection by controlling the order in its answer, but it is limited to choosing from among the codecs the offerer proposed. Different codecs have different characteristics that make them suitable for different scenarios. Opus is the preferred audio codec in WebRTC because it's specifically designed for interactive real-time applications, handling everything from low bitrate voice to high-quality music. For video, VP8 is widely supported and royalty-free, while VP9 offers better compression but requires more computational power. H.264 remains popular due to hardware acceleration support in many devices, though it has patent licensing considerations. The negotiation process ensures that peers use the best codec they both support, balancing quality, computational requirements, and compatibility. DTLS-SRTP Security Layer. Security is fundamental to WebRTC, not an afterthought or optional feature. Every WebRTC connection uses DTLS-SRTP to provide encryption and authentication for media streams. DTLS stands for Datagram Transport Layer Security, and SRTP is Secure Real-Time Transport Protocol. Together, they create a robust security framework that protects your communications from eavesdropping and tampering while working over unreliable UDP transport. DTLS is essentially TLS, adapted for datagram protocols like UDP, while TLS requires a reliable ordered byte stream, like TCP provides. DTLS modifies the protocol to work with packet-based transport, where packets might arrive out of order, be duplicated, or go missing entirely. In WebRTC, DTLS serves two critical purposes. First, it establishes the encryption keys that will be used for media encryption. The DTLS handshake uses public key cryptography to securely agree on symmetric keys without the risk of interception. Second, DTLS authenticates the peers to each other, ensuring you are actually connected to who you think you are connected to. The authentication aspect is particularly interesting in WebRTC. Instead of relying on certificate authorities like web browsers do for HTTPS, WebRTC uses self-signed certificates combined with fingerprint verification. During the connection setup, each peer generates a self-signed certificate. The fingerprint of this certificate, which is just a cryptographic hash, is included in the SDP exchange and transmitted through the signaling server. When the DTLS handshake occurs, each peer verifies that the certificate presented by the remote peer matches the fingerprint they received through signaling. This binds the security of the media connection to the security of your signaling channel. Once DTLS establishes the keys, SRTP uses them to encrypt the actual media packets. SRTP is a profile of RTP specifically designed for encrypting audio and video streams. It encrypts the payload of each RTP packet while leaving the RTP header unencrypted so routers can still perform their duties of routing, and QoS-SRTP also provides authentication for each packet, allowing the receiver to detect if packets have been tampered with in transit. This combination of encryption and authentication ensures that WebRTC communications remain private and unmodified from end to end. Basic WebRTC connection flow. Let's walk through the complete process of establishing a WebRTC connection from start to finish. This will tie together all the concepts we've discussed and show you how they work together in practice. Understanding this flow is essential for debugging WebRTC applications and optimizing the connection establishment process. The process begins when both peers connect to your signaling server. This connection can use any protocol you choose, but WebSockets are popular because they provide low-latency bidirectional communication. Once connected to signaling, Peer A decides to initiate a call to Peer B. Peer A's browser creates an RTCPeerConnection object and begins gathering ICE candidates by contacting STUN and TURN servers. Simultaneously, Peer A creates an SDP offer using the createOffer method. This offer describes what media streams Peer A wants to send, what codecs it supports, and includes preliminary network information. Peer A sets this offer as its local description using setLocalDescription, which locks in these parameters for the local side of the connection. The offer is then sent through the signaling server to Peer B as ICE candidates are discovered by Peer A, each one is immediately sent through signaling to peer B as well. This parallel transmission of the SDP offer and ICE candidates allows the connection process to proceed efficiently rather than waiting for all candidates before continuing. When peer B receives the offer through signaling, it creates its own RTCPeerConnection object and sets the received offer as its remote description using setRemoteDescription. This tells peer B what peer A is offering. Peer B then creates an SDP answer using createAnswer, which responds to the offer by indicating what peer B can support. Peer B sets this answer as its local description and sends it back to peer A through signaling. Like peer A, peer B is also gathering ICE candidates, which it sends to peer A as they are discovered. When peer A receives the answer, it sets it as its remote description. Now both peers have a complete picture of the session. As ICE candidates arrive from the remote peer, each peer adds them using addICE_candidate. The ICE framework begins testing connectivity between the various candidate pairs, trying to find working paths between the peers. Once a candidate pair succeeds in establishing connectivity, the ICE state changes to connected, and media can begin flowing. The entire process typically completes in just a few seconds, resulting in a peer-to-peer connection carrying encrypted audio and video streams. RTCPeerConnection lifecycle. The RTCPeerConnection object goes through a series of well-defined states as it establishes and maintains a connection with a remote peer. Understanding these states is crucial for building robust WebRTC applications because they tell you exactly what is happening at each stage of the connection process. The lifecycle begins when you create a new RTCPeerConnection object and continues through various states until the connection is eventually closed. The signaling state tracks the progress of SDP offer-answer negotiation. It starts in the stable state, meaning no negotiation is in progress. When you call createOffer or createAnswer, the state transitions through have local offer or have remote offer respectively, indicating that an offer has been created or received but not yet matched with an answer. Once the answer is set, the state returns to stable, signifying that negotiation is complete and both peers have agreed on the session parameters. The ICE connection state provides insight into the network connectivity between peers. It progresses through several stages. New, when ICE gathering has not started. Checking, while the ICE framework tests candidate pairs. Connected, when at least one working path has been found. And completed, when all components have found successful paths. If all candidate pairs fail, the state becomes failed. There is also a disconnected state that occurs if connectivity is temporarily lost, but might be recoverable. The connection state is a higher-level view that combines ICE and DTLS states. It moves through new, connecting, connected, disconnected, failed, and closed states. This state is often the one you will monitor most closely in your application because it provides a clear picture of overall connection health. When the connection state becomes connected, you know media can flow. If it becomes failed, you know the connection is irretrievably broken and you need to start over or notify the user. RTCDataChannel communication. RTCDataChannel provides a powerful mechanism for sending arbitrary data between peers beyond just audio and video streams. Think of it as a WebSocket connection, but peer-to-peer. This channel can carry text messages, binary data, files, game state updates, or any other information your application needs to exchange. The beauty of DataChannel is that it uses the same peer-to-peer infrastructure as MediaStreams, so it benefits from low latency and does not require separate server infrastructure. Creating a data channel is straightforward. One peer calls create data channel on their RTCPeerConnection, giving the channel a label to identify it. This peer becomes the channel creator. The remote peer receives a data channel event when the channel is established, providing them with the channel object they can use to send and receive messages. Both peers can then exchange messages using the send method and receive them via message events. The API is deliberately similar to WebSockets to make it familiar to web developers. Data channels support different delivery modes through two key configuration options: ordered and max retransmits or max packet lifetime. By default, data channels provide reliable, ordered delivery similar to TCP. Messages arrive in the same order they were sent, and lost packets are retransmitted automatically. However, you can configure unreliable delivery for use cases where low latency matters more than reliability. In unreliable mode, you can specify either a maximum number of retransmission attempts or a maximum time to spend trying to deliver a message. This is perfect for applications like gaming where old state updates become irrelevant quickly. The buffered amount property helps you manage flow control when sending large amounts of data. This property tells you how many bytes are queued for transmission but have not been sent yet. If you are sending data faster than the network can transmit it, buffered amount will grow. By monitoring this value, you can implement backpressure mechanisms, pausing your sends when the buffer gets too large and resuming when it drains. This prevents memory exhaustion and ensures smooth data transmission even when sending large files or continuous streams of data. Media constraints and get user media. The get user media method is your gateway to accessing the user's camera and microphone, but it's much more powerful than simply turning on devices. Through the constraints parameter, you can precisely specify what kind of media you want to capture. Constraints let you control resolution, frame rate, audio sample rate, echo cancellation, noise suppression, and many other parameters. Understanding how to use constraints effectively is key to delivering the best possible user experience. Constraints are expressed as a JavaScript object with separate sections for audio and video. Each section can be a simple Boolean to enable or disable that media type, or an object containing specific requirements. Within these objects, you can specify ideal values for properties you would prefer, or required values for properties that must be met. For example, you might require a minimum video width of 640 pixels but ideally prefer 1280 pixels. The browser will try to satisfy your ideal constraints but will fall back to acceptable values if necessary. Common video constraints include width and height for resolution, frame rate for how many frames per second to capture, and facing mode to select between front and rear cameras on mobile devices. The facing mode constraint is particularly useful, accepting values like user for front-facing cameras or environment for rear-facing ones. You can also constrain aspect ratio to maintain specific video proportions, which is helpful when you are designing UI that expects particular dimensions. Audio constraints offer sophisticated processing options. The echo cancellation constraint enables or disables acoustic echo cancellation, which removes the sound of the remote participant's voice from your microphone capture. This is usually enabled for voice calls but might be disabled for music applications where you want to capture all sound. The noise suppression constraint reduces background noise, cleaning up the audio signal. The auto gain control constraint automatically adjusts the microphone input level, ensuring consistent volume even as the speaker moves closer or farther from the microphone. These processing features can dramatically improve audio quality in real-world conditions. Simulcast and SBC. When building large-scale WebRTC applications like video conferences with many participants, bandwidth becomes a critical constraint. Not all participants have the same network conditions or display capabilities. Some might be on high-speed fiber connections with large displays, while others are on mobile networks with small phone screens. Simulcast and scalable video coding, or SBC, are techniques that address this challenge by allowing a single video stream to serve multiple quality levels. Simulcast means the sender encodes the same video stream at multiple different resolutions and bitrates simultaneously. For example, a sender might create 3 versions: a high-quality 1080p stream at 2 megabits per second, a medium 720p stream at 1 megabit per second, and a low 360p stream at 300 kilobits per second. All 3 encodings are sent to a selective forwarding unit, or SFU, which is a media server that forwards video streams to receivers. The SFU can then choose which quality level to forward to each receiver based on their network conditions and display size. A receiver on a poor connection gets the low-quality stream, while one with abundant bandwidth gets the high-quality version. The advantage of simulcast is that quality adaptation happens at the SFU, rather than through re-encoding. The SFU simply selects which pre-encoded stream to forward. This is a lightweight operation that requires minimal CPU resources. The sender does pay the cost of encoding multiple streams, but modern hardware and efficient codecs make this feasible. Simulcast works with any codec and is widely supported across WebRTC implementations, making it a practical solution for real-world deployments. Scalable video coding takes a different approach by encoding a single stream with multiple dependency layers. An SBC encoded stream has a base layer that provides minimum quality, plus one or more enhancement layers that progressively improve quality. The enhancement layers depend on the base layer, forming a hierarchy. The SFU can forward just the base layer for bandwidth-constrained receivers, or include enhancement layers for receivers that can handle more data. SBC is more bandwidth efficient than simulcast because the layers share encoding information, but it requires codec support and is currently best supported with the VP9 codec. The choice between simulcast and SBC depends on your specific requirements and target platforms. Selective Forwarding Unit SFU. As WebRTC applications scale beyond simple peer-to-peer calls to multi-party conferences, the mesh topology where every participant connects to every other participant becomes impractical. In a mesh network with n participants, each participant maintains n-1 peer connections and uploads their media n-1 times. When you have 10 people on a call, each person is managing 9 connections and uploading their video 9 times. This quickly overwhelms client upload bandwidth and CPU capacity. The Selective Forwarding Unit architecture solves this problem. An SFU is a media server that sits in the middle of a multi-party call. Instead of connecting to every other participant, each client connects to the SFU with a single peer connection. Clients upload their media once to the SFU, and the SFU forwards it to all other participants. This dramatically reduces the upload burden on each client, changing it from n-1 uploads down to just 1. The SFU handles the fan-out of media streams, leveraging server-grade bandwidth and processing power to efficiently distribute streams to all participants. The key characteristic that makes an SFU different from a traditional media server is that it doesn't decode or re-encode the media streams. When the SFU receives an RTP packet containing video or audio, it examines the packet headers but leaves the payload untouched. It then forwards the packet to the appropriate recipients. This forwarding operation is much lighter weight than transcoding, allowing a single SFU server to handle hundreds of participants. The SFU might change some RTP header fields, like the SSRC identifier to distinguish between different senders, but the encoded media itself passes through unchanged. Modern SFUs add intelligence through selective forwarding. Rather than blindly forwarding all streams to all participants, the SFU can make decisions about which streams to forward based on various factors. It might implement active speaker detection, forwarding only the video of whoever is currently speaking to reduce bandwidth. It can implement spatial simulcast, choosing appropriate quality levels for each receiver. Some SFUs support features like video recording, where they selectively forward streams to a recording component. Popular open-source SFU implementations include Janus, Jitsi VideoBridge, and MediaSoup, while commercial options include services from Agora, Vonage, and Daily.co. Network Quality Adaptation. Network conditions on the Internet are variable and unpredictable. Bandwidth fluctuates, packet loss occurs, latency spikes happen. WebRTC includes sophisticated mechanisms to adapt to these changing conditions and maintain the best possible quality under current circumstances. These adaptations happen automatically, but understanding them helps you build applications that handle network variability gracefully. Bandwidth estimation is the foundation of network adaptation. WebRTC continuously measures the available bandwidth by analyzing packet loss, delay, and successful transmission rates. It uses algorithms like Google Congestion Control, or GCC, which combines loss-based and delay-based signals to estimate capacity. When packet loss increases or delays grow, the estimator concludes that the network is congested and reduces the estimated bandwidth. When conditions improve, it gradually probes for more capacity by increasing the estimate. This bandwidth estimate feeds into encoder rate control. Once bandwidth is estimated, the video encoder adjusts its output bitrate to match available capacity. If bandwidth decreases, the encoder reduces its target bitrate by lowering the frame rate, reducing the resolution, or increasing compression. Modern video codecs are designed for this kind of dynamic adjustment. If conditions worsen severely, WebRTC might stop sending video entirely and continue with audio only, since voice requires much less bandwidth than video. When bandwidth improves, the process reverses, gradually increasing quality as more capacity becomes available. The GetStats API provides visibility into all these adaptation mechanisms. You can query statistics about bandwidth estimates, packet loss rates, jitter, round-trip time, frame rates, and bitrates. This information is invaluable for debugging connection quality issues and understanding how your application performs under real-world conditions. You can use these statistics to implement application-level adaptations too, like displaying quality indicators to users or automatically switching between video and audio-only modes based on network conditions. The Stats API returns a complex object with dozens of metrics, so it's worth studying the specification to understand which metrics matter for your use case. Perfect negotiation pattern. One of the challenges in WebRTC is handling the offer-answer negotiation in a way that is symmetric and gracefully handles race conditions. The perfect negotiation pattern is a design approach that elegantly solves this problem. It allows either peer to initiate negotiation at any time without worrying about collision detection or complex state management. This pattern has become a best practice for implementing WebRTC signaling logic. The pattern designates one peer as polite and the other as impolite, but this designation is arbitrary and does not affect the actual connection. The polite peer will back down if a collision occurs, where both peers try to negotiate simultaneously. The impolite peer simply proceeds with its negotiation. This asymmetry breaks the deadlock that would otherwise occur. In your application, you might decide that the caller is always impolite and the callee is always polite, or use any other consistent rule to assign these roles. The implementation revolves around the negotiation needed event. When WebRTC needs to renegotiate the connection, perhaps because a new track was added or parameters changed, it fires this event. Your code responds by creating a new offer and sending it through signaling. The key innovation in perfect negotiation is how it handles incoming offers. If the local peer is in the middle of negotiation and an offer arrives, the polite peer will roll back its local negotiation and accept the incoming offer. The impolite peer will ignore the incoming offer and continue with its own negotiation. Perfect negotiation greatly simplifies WebRTC application code. You do not need complex state machines tracking who offered when, or manual collision detection logic. The pattern handles all edge cases automatically, including scenarios where both peers try to add tracks simultaneously or where rapid renegotiations occur. It makes your signaling code more maintainable and less error-prone. The WebRTC specification documentation includes reference implementations of perfect negotiation that you can adapt for your applications. Screen sharing with WebRTC. Screen sharing has become an essential feature for remote collaboration, education, and support applications. WebRTC makes screen sharing straightforward through the getDisplayMedia API, which works similarly to get user media but captures screen content instead of camera and microphone input. The API provides fine-grained control over what can be captured and how users select what to share. When you call getDisplayMedia, the browser presents a picker UI to the user where they can choose what to share. Depending on the browser and operating system, users can select an entire screen, a specific window, or individual browser tabs. This user-controlled selection is a critical privacy feature. Unlike getUserMedia, getDisplayMedia always requires a user gesture, meaning you must call it in response to a button click or similar user action. You cannot start screen sharing without explicit user interaction, preventing malicious sites from silently capturing screen content. The MediaStream returned by getDisplayMedia contains video tracks representing the captured screen content, and optionally audio tracks if the user chose to share system audio or tab audio along with the video. You can add these tracks to an existing RTCPeerConnection just like camera tracks. One important difference is that screen share video tracks typically have much higher resolutions than camera video, often running at full monitor resolution like 1920 by 1080 or even 4K. You need to ensure your bandwidth constraints and encoder settings can handle these larger frames. Screen sharing introduces some unique considerations. Frame rates are often lower than camera video, perhaps 5 to 15 frames per second instead of 30 frames per second, because screen content changes less frequently than real-world video. Some applications implement smart optimizations, like only encoding and sending changed regions of the screen rather than the entire frame every time. You should also handle the ended event on the screen share track, which fires when the user stops sharing through the browser UI. This allows you to clean up the connection and update your application UI to reflect that sharing has stopped. WebRTC security considerations. Security is paramount in WebRTC because real-time communications often involve sensitive personal or business information. The protocol includes strong security by default, but developers must understand the security model and their responsibilities to build truly secure applications. WebRTC's security spans multiple layers, from media encryption to signaling protection to user privacy controls. At the media layer, WebRTC mandates encryption. All audio, video, and data channel communications must be encrypted using DTLS-SRTP. There is no way to disable this encryption. This protects media content from eavesdropping as it traverses the internet. However, the security of the media connection depends critically on the security of your signaling channel. Remember that DTLS authenticates peers using certificate fingerprints exchanged through signaling. If an attacker can tamper with your signaling messages, they could perform a man-in-the-middle attack on the media connection. Therefore, you must use TLS to secure your signaling channel, ensuring that SDP messages and ICE candidates cannot be intercepted or modified in transit. User privacy controls are another critical aspect. Browsers require user permission before accessing cameras and microphones. This permission must be explicitly granted, and users can revoke it at any time. Your application must handle permission denial gracefully and respect user choices. When permission is granted, browsers typically display indicators showing that the camera or microphone is active, preventing invisible surveillance. For screen sharing, browsers enforce even stricter controls, requiring per-session permission and providing clear UI showing what is being shared. You should also consider application-level security concerns. Implement authentication in your signaling server to ensure users are who they claim to be. WebRTC future and conclusion. WebRTC continues to evolve with new features and improvements being standardized and implemented. Recent additions include insertable streams, which give developers access to raw encoded frames for implementing custom encryption or processing. A V1 codec support is being added, offering better compression than VP9. Web transport and web codecs APIs are emerging to provide lower-level control over transport and encoding. The WebRTC community remains active, with ongoing work to improve performance, reduce latency, and add capabilities. The applications of WebRTC extend far beyond simple video calling. We're seeing WebRTC used in telemedicine for remote patient consultations, in education for virtual classrooms, in customer service for video support, and in IoT for device monitoring and control. Gaming companies use WebRTC data channels for low-latency multiplayer communication. Broadcasting services use it for interactive live streams. The technology has proven versatile and robust across diverse use cases. Building production WebRTC applications requires attention to infrastructure and operations. You need to plan for TURN server capacity and costs. You must implement monitoring and analytics to understand connection quality and failure rates. Consider using managed services for STUN and TURN infrastructure, or for entire WebRTC platforms if you want to avoid operational complexity. Test thoroughly across different networks, devices, and browsers to ensure compatibility. Design your signaling for reliability and scalability. WebRTC has fundamentally changed how we think about real-time communication on the web. By providing standardized APIs directly in browsers, it has democratized the development of communication applications. What once required specialized expertise and proprietary software can now be built with standard web technologies. As the technology continues to mature and new capabilities are added, we can expect even more innovative applications that leverage real-time peer-to-peer communication. Thank you for your attendance. Please consider subscribing to the channel.